All right, so I'm going to continue with class today with a problem on actually calculating. So before this, I didn't really show you guys any calculations. I kind of showed you how to graph change when you use different kinds of solution. And we talked about the formulas, the IM, and all that stuff. And now let's go ahead and actually try to calculate some stuff, okay? Now, you'll see different kinds of questions when you do your homework. DSM is extra credit, yes. That's why you gotta do it. Everything that says EC on there is extra credit. And if you notice, at the end of the semester, the extra credit on there, I actually made more of them. They changed them this semester, so there's more extra credit assignments on there. So it's by topic, so it's gonna be basically topic specific when you do those extra credit. Okay, so let's go ahead and work on this question. It says calculate the freezing point. Oh yeah, I was saying like when you do your homework, you'll see different kinds of problems. Homework, quiz, and then definitely when you're ready to take the test, you do the practice test, you'll be able to see different kinds of questions as well. Freezing point of a 1.7 molality aqueous solution of ethylene glycol, C2H6O2, that's ethylene glycol right there. And the KF for water, because it's aqueous, so we get the KF for water. We're going to use 1.86 Celsius per molality. Okay, so it's very important to not write moles using M, because that's absolutely wrong, incorrect. Okay, when you want to say moles, you use MOL to symbolize mole. The real word is MOLES, moles, but you know, the short abbreviation for mole is MOL. M here is for molality, or if we were talking measurements of length, it could be meter as well. But so we don't need an extra M here for moles, okay? So this is molality right here. All right, so our formula, if you remember, delta TF, okay, equals to I M KF, okay? Do you have an I here if it's ethylene glycol? Ethylene glycol is not an ionic compound. How can you tell it's not ionic? Is there a metal in here? Remember Chem 1, we said ionic stuff has metal, cation, and anion, that's non-metal, and then they have plus and minus charges. This one here is completely non-metal, and they are probably formed by using all covalent bonds, right? So you learn how to draw out Lewis dot structures. So this one here is non-ionic, so the I here doesn't really matter. We can just pretend it's 1 because it doesn't split, right? So we can say, okay, this one's 1, there's no I, it just kind of disappears, right? But I can put 1 in its place. Molality is right here, okay? 1.7. I like to write my units down with it so I know what unit I end up with for my answer. So it says KF here if I use 1.86. So then I know my molality cancels off, okay? And all you do, in your calculator, it would be really easy, 1.7 times 1.86. You end up wanting to keep just 2 suffix, so you get 3.2 Celsius. Now, remember, I said this delta TF is an absolute value. But this is not the freezing point, is it? This is the freezing point depression. This is how much it's gone down by. Because we know freezing point goes down, boiling point goes up, okay? So because they asked for the freezing point, they didn't ask for a freezing point depression. The answer for freezing point is actually what? Well, the original freezing point of water was, you should know that, 0, right? Okay, so standard is going to be 0.00 Celsius, okay, for water. This is for pure water, the original. And then it says we went down by 3.2, so it has to go down by 3.2. Well, if it goes down by 3.2, you're going to get your answer as negative 3.2 Celsius. And that will be your freezing point. So this is your final answer right here. Okay, so it's very important to read the question. Now, if they ask you what is the freezing point depression, that would be the answer. If they ask you what's the freezing point, well, it's not going to be that one, it's going to be the negative one. And both answer choices are going to be on there, okay? If it's multiple choice, both of them will be on there, so you have to read carefully what they're asking for, all right? Okay, so let's go to another question now. Let's see. What mass of ethylene glycol C2H6O2. So what mass, that means they'll need to give you the molar mass, or you can calculate it, because at some point you're going to need molar mass. In grams must be added to 1.0 kilograms of water to produce a solution that boils at 105.0 Celsius. Molar mass of C2H6O2 is 62.07 grams per moles. Let's go ahead and give you the KB because we're talking about boiling point now. So KB of water, okay? This is using water as a solvent, so you use KB of water. So for water, the KB value is 0.512 Celsius per molality. So just looking at this number here, you know how the freezing point was 1.86? The KF was 1.86, this is 0.512. So that means the boiling point is shifting at a smaller increment than the freezing point would be, right? Because the freezing point goes down, every time you have one molality is 1.86. The boiling point only goes up 0.512 per one molality. So that can kind of show you the chart. The freezing point actually will spread faster, going down fatter. So let me put the graph here. When I drew it, it's not really accurate here. You see how mine is kind of like the same size here? Really, if you looked at water, this one should be bigger than that, because this is 1.86 per one molality. This is 0.512. Okay, so just an observation here, because sometimes there are questions that ask you something about the freezing point if they give you information about the boiling point. They're saying, well, if you know, if it went up by 5 degrees in boiling point, how much would this solution go down for the freezing point? It would be bigger than 5 Celsius. You guys agree? Because the KF of water is bigger. Okay, we can actually try to do that after this just to show you, okay? So in this case here, it's 105.0 Celsius. That's the new boiling point. What was the original boiling point of water? 100. Okay, so how much did it go up by? So your delta TB here is 5.0 Celsius. Do we agree? So same idea there earlier. If they ask you for the delta TF, it was 3.2, but the freezing point was really negative 3.2. Okay, so the delta TB here is 5.0 Celsius because the boiling point was 105. Because you start from 0 and you start from 100, and whatever increase in from 100, that's your delta TB. Whatever decrease from 0, that's your delta TF. Okay, so that's my value right here for delta TB. Now, what was my formula again? It was delta TB equals to I m KB. Okay, so all I gotta do is put this 5 down here. And then I is nothing because it doesn't split, so I can just ignore it, pretend it's 1, okay? M is molality. Now I don't have M, and M molality here will help me get the grams I need, okay? Because I know I have 1 kilograms of water, so I need to find molality first. Okay, but what's my Kb? 0.512 Celsius per molality. Okay, so let's go and calculate what the molality answer will be. It will be just simply 5 divided by 0.512 here. So we get 9.77. So I'm going to underline the second 7 because I know I really should be giving 2 sig here. So it's moles of solute, right? Which is ethylene glycol over kilograms of solvent, which is water. So that tells me that's my concentration. Every time you have a concentration or density or something like that, that has 2 units here, you can literally write, that means I can find 9.77 moles of solute, which is ethylene glycol. And every time I find exactly 1 kilograms, well, I shouldn't have written 1.0, it's exactly 1, so I can just write 1. This one here has unlimited sig figs. Okay, I'm going to use this to ask how many grams I need, because I know I have 1 kg. So obviously if you have 1 kg, if you didn't have 1 kg, if you had like 10, 100, 200, whatever the value is, all you do is you take the 1 kg of your water, you multiply the amount of your water, and you work it with your molality term. So I'm going to cancel out water, so 1 kg of water goes on the bottom. This is from the molality here, right here. And I'll put 9.77 on the top. So basically it's just taking the molality times the kilograms of water that you know you have. That will give you grams, that will give you moles of ethylene glycol. And if you want it grams, what do? You cancel off the moles, you use the molar mass. So when you see the molar mass here, I can write, well, every time I have 1 mole, mole of ethylene glycol, it weighs 62.07 grams. So I'm going to go ahead and cross off the moles, put the moles on the bottom. So that means divide by the moles on the bottom, and really it's just multiplying with the molar mass. Okay, and that should give me grams, because I use the kilograms to find out how many moles, and from the moles, with using the molar mass, I can get the grams. You end up getting, so we wanted just 2 sig figs here. So you get 6.1 times 10 to the power 2 grams of ethylene glycol. Okay, any questions so far? Are we all good? All right, so based on this question here, let's say we use the same exact ethylene glycol that went up by 5 degrees. Can you predict what the freezing point will be? Okay, so we can try to do that, just an extra layer. So do you think the freezing point will be less than negative, well, would it be negative 0.5, negative 5.0? Will it be exactly negative 5.0? It won't be, because the KB here is smaller. So basically, if you take I times M times KB, it gives you how fat the chart expands and how big the delta TB will be. But because our KF is so much bigger than the KB, this number here, the 5 degrees, is going to change, okay, for your delta TF. So I'll write a question out. So using this same solution, predict the freezing point of the solution. Okay, our KF is 1.86. So basically, you need to find the delta TF first, and then you can get the new freezing point. And delta TF is IMKF. We want to use the exact same solution, so the I is 1, M is 9.77, because we just calculated that, right? And then Kf would be 1.86. So here's the difference. You see how on the top here is IMKF and their 9.77 is the same, I the same, and then this value here is different. You see that? So because of that value's difference, your delta TF is going to be a bigger value. So let's see how much that is. You get like 18 point, it's 1722, but we don't have to keep all that. I'm just going to write it down. But really, you're just going to keep the second number. So your real freezing point will be basically 18 degrees smaller than your original, which is 0, right? So what's your freezing point now? It's going to be negative 18 degrees Celsius, or 18.2. All right, so that's what, like, you see how it was a -5, it's -18 versus +5. That's because of the Kf being bigger than the Kb for the same kind of solvent and solution. Okay, all right, so let's
I have a question. Yeah. Why does the freezing point change becomes negative? What's the logic behind it?
We talked about this in the class before this. Basically, freezing point based on the phase diagram, you can see anytime you make a solution, the diagram expands. And you can find a freezing point along here. So we talked about how to find a boiling point, the normal boiling point, freezing point, normal freezing point. This was from last class. So if you don't remember or didn't see this one, you need to go back and watch it. But basically that's why it goes down here. The freezing point will go down, the boiling point will go up, and that's why we put ice on the road. We went through that explanation in the previous class. Okay, do you guys remember this part here? That's why the freezing point goes down, okay? And the topic, it says freezing point depression and boiling point elevation. So the topic itself talks about this chart expanding, okay? So when it goes down here, that's why we have a number that's smaller. You see, the more it shifts, the more negative it becomes. But on the same solution, from 100 from water, it goes up, it increases. Okay, it's based on this chart here. Everyone good here so far? All right, because I'm going to talk about the next part. So based on this here, we talked about vapor pressure. Remember this, the vapor pressure curve? And what's the definition of vapor pressure? You guys remember that? So I talked about how if you have a beaker or any system that it has evaporation and condensation happening at the same time. And then when it reaches equilibrium where it stops, the rate of evaporation equals the rate of condensation, it looks like the water amount versus the gas amount is not changing anymore. So the amount of gas that's left at dynamic equilibrium here will create a pressure, and that's called the vapor pressure. Okay, so the vapor pressure of the liquid is on here. This is the vapor pressure curve of the water. Now we also said when the vapor pressure equals to the external pressure, that's when we find a boiling point. So this whole curve here is full of boiling points, and at the 1 atm we call it the normal boiling point. Okay, now we want to talk about specifically how to calculate a vapor pressure. This was a liquid. We want to talk about calculating vapor pressure of solutions now. Okay, so how does a solution's vapor pressure compare to an original solution? So I'm going to show you a picture here from our slides. Well, I guess it's not the picture yet. Right here. So this is slide number 43, okay? Now, slide number 43, it shows you originally you got water. We'll just talk water, simpler, easier to imagine. So we have just water here, and water, you close the beaker, eventually the rate of evaporation and condensation equals out, they reaches dynamic equilibrium, you have 1, 2, 3, 4, 5, 6, 7. I think it's about 12 in here, right? So those 12 things of gas is going to create a vapor pressure, and that's a vapor pressure of pure water. Okay, so it should be, so the more gas you have, the more vapor pressure it will be. Okay, now say you now introduce something into your solution. So they said they put a solute in there, a non-volatile solute. That means the solute does not turn to gas. Okay, the solute can't automatically turn to gas. Kind of like if you put sugar in water, does the sugar just turn to gas? The sugar can't turn into gas. So that's an example, right? Non-volatile. So the sugar stays in the water. And the water's like, oh, I'm so happy I have new friends to bond with. Well, it's not really bond, it's intermolecular forces. They're kind of talking to each other. There's an attraction between water and the solute. Okay, so because of that extra new attraction, there's new buddies in there to pair with. What happens is when you put the new solute in, more of the water will stay in a liquid phase and less of them will be in gas phase because there's more reason to stay in a liquid. There's more buddies there now. Okay, now because of that, you count 1, 2, 3, 4, 5, 6, 7, 8, 9. It's less than the original without if you put a solute. So because the number is now dropped, okay, when you have a solution, vapor pressure of a solution is always, always, always smaller than the vapor pressure of the original solvent. Are we clear? It's always going to be a fraction of the solvent because the solvent is original, and when you make it into a solution, the solution's vapor pressure will be always smaller than the original solvent that you had. Okay, so that's the idea. So this is what we call Raoult's law. Go ahead and write it out for you guys, but it also says on the slide before that. You just have to remember it says here, because of the new attractions that's being formed, vapor pressure of solution is lower than vapor pressure of a pure solvent. Okay, so remember that from slide number 42. So I want to talk a little bit about Raoult's law and what it says. I'm going to go ahead and write it out for you guys, and we'll do some calculations. We'll do different types of Raoult's law calculations, okay? It's a little bit different from what you might have seen in Chem 1 if you saw it before. We're just going to build on it, basically. So, let's spell it. Okay, so we have basically what we just said on the picture. We said solvents in the solution. The vapor pressure of the solvent in a solution is going to be basically the solvent is part. So in your solution, you have solvent, you have solute, right? I'll write it out. Solute plus solvent. Oh, I have an extra V. Equals to solution. Okay, so now we're talking about just the solvent portion. The solvent in the solution will be equal to the mole fraction of the solvent times the original vapor pressure of the solvent. So the original is symbolized with this not sign here. Okay? So that's mole fraction, in case you guys. So we're always saying it's going to be smaller than original, correct? So we have the solvent part, and then if you have to get a total solution, so we get total P of total of the solution. You got to do the P of the solute and the P of the solvent, which that was the P of the solvent up here, okay? So if you have the total solution, you got to do the solute and the solvent. Now, a lot of times our solutes don't turn to gas. So that part turns to 0, it doesn't exist. But if you have a solute that can turn to gas, for example, if you have liquid and liquid, both of them, they're solute and solvent, both of them liquid can turn to gas. So you'd have to calculate the solute portion and the solvent portion. So you need the formula for solute. So P of solute in the solution if you needed to do that part, okay, this is only if the solute can turn to gas. Most of the time it doesn't. It should tell you. How can you tell if it turns to gas? Well, if it turns to gas, they have to give you the original vapor pressure for you to calculate. If they don't give it to you and they don't mention it, and then you don't know if it does or not, then it probably doesn't, okay? If it has an original vapor pressure, then you're like, oh yeah, that one's gonna turn to gas. So this is X of solute, mole fraction of the solute, plus, not plus, multiply with P original of my solute. So it's always compared to the original. It's always a fraction of it, because anytime you go to a solution, it gets smaller, okay? So the mole fraction becomes important because it tells you exactly how much smaller it will be. So the first type of calculation I'm going to do is we're going to do a calculation where P of the total solution, they ask you for the solution, P of the solution, but the solute part does not turn to gas. Okay, it doesn't turn to gas, so that term completely gets dropped out. So in the end, your P of your solution literally equals to your P of solvent, which equals to a mole fraction of the solvent times original vapor pressure of the solvent alone. Okay, so if your solute does not turn to gas. So we'll do that kind of example first, okay? So the first example, we also have underneath the solute portion that doesn't turn to gas, we have ionic and non-ionic. So we're gonna go ahead and do the non-ionic one first, okay? So we're going to calculate vapor pressure of a solution. Where the solute is non-ionic and non-volatile. Okay? So I'll write the question out. So that's basically non-ionic, non-volatile. You don't have the solute portion. You're only going to do the solvent. So the question is calculate the vapor pressure at 25 degrees Celsius of a solution containing 99.5 grams of sucrose. And sucrose formula is C12H22O11 and 300.0 ml of water. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. Assumed density of water is 1.00 grams per mils. Molar mass of glucose is 342.3 grams per moles. Molar mass of water is 18.02 grams per moles. Okay? All right, so let's see. Now we have 99.5 grams of sucrose, 300 mils of water. You mix them up together, you make a solution, okay? So from here, they told you the original vapor pressure of water is at this temperature, 25 degrees, is 23.8. They want you to calculate the vapor pressure of the solution that's made here. So from sucrose here, they don't tell you the original vapor pressure of sucrose because sucrose does not turn to gas phase and it doesn't have a vapor pressure because of that. Okay, So this is how you can tell based on the P of the solution earlier that we talked about. Raoult's law says that if you have a P of solution, you have to add up the solute part and the solvent part. But since our solute doesn't even turn to gas, that part becomes nothing. Okay, so how can you tell? They didn't tell you the vapor pressure original sucrose is blah, blah, blah. There's nothing there, so that means it doesn't turn to vapor here. That's a hint, okay? Unless they're asking you to calculate, then they'll have some terms about it they'll tell you about. You just have to read the question. So in this case here, we're gonna do just a solvent. So how is it, what's the formula for solvent? So P of the solvent in a solution is going to be mole fraction of the solvent times the original vapor pressure of the solvent. Now they gave us the original vapor pressure of the solvent, it's this guy. So you have to remember what torr is. Torr is a unit of pressure, T-O-R-R, right here. So all you gotta do now is find that term. You have to find the mole fraction of your solvent, which is why we were doing all those conversions in the class before this. We were doing like mole fraction, mole percent, mass percent, you know, stuff like that, molality, because we're using it here. So mole fraction of water. So I'm just gonna write, the solvent here is water, so mole fraction of water is gonna be moles of water over moles of water plus sucrose. Okay, so then we get to calculate the moles. So let's go ahead and do that. Do we have the grams of sucrose? Yes. Do we have the molar mass of sucrose? Yes. Can you get the grams of water from the mils if they gave you the density? Yes, you can do that, right? And they're so nice, it's 1, so it's literally the same number. Okay, so we use that. Once you get mils, you turn to grams. Grams, you can turn into moles. So our job is to find moles of water and moles of sucrose. Okay, so that we can find this mole fraction, put it up here, and we'll get the answer. So let's go ahead and start with the sucrose. It's 99.5 grams of sucrose. 1 mole of sucrose was like 342.3. So at this point here in this class, you should not be questioning on how to get from grams to moles. That is no longer an issue. If this is still an issue, then it might be time to review a lot of stuff from Chem 1 because this is going to build on top of it. This class assumes you know how to do that stuff already, okay? So 1 mole is 342.3. Okay, so let's see how many moles that is. We want to keep 3 sig figs, right? I'll just underline the third number. So this is 2907. So it's 291 really, but I'm not going to round until the end. That's 1. Let's do the water. So I'm going to go ahead and show you the density step from mils to grams, where density is 1.00 grams per 1 mil of water. And then I can take 1 mole of water weighs 18.02 grams. So I can get my moles of water here. And I'm going to keep 3 sig figs here because of 1.00 here. 16, all right, 6.5, underline the 6 here. That's moles of water. This is moles of sucrose. So all we do is plug those things up here, get the mole fraction. I'm going to put it back up here, okay? So it's water goes on the top, so 16.65 moles of water, and then on the bottom is 16.65 plus 0.2907. And then let's see what we get for our mole fraction. It should be really close to 1 because this is such a big number, not such small. So it's 0.0 9828. We'll just keep it there. So that's my mole fraction here. So I'm going to calculate that up here. I'll put that in here, 0.9828 times 23.8 and see what answer you get. You want to keep 3 suffix here, so you get 23.4. So if you guys are taking lab, when you calculate stuff for your post lab, I want you to not round until the last step. Okay? Keep all your numbers, write it down, underline it. So what I like to do for a lab question is to try to set up the math so I can punch all the numbers in at one time and then round only at the end. Okay, if you have multiple steps, keep the numbers in there with you and recall that number back. Okay, so that's our answer right here. So put a mark right there. That should be our answer. Now again, I expected it to be less than 23.8 because I know it's a fraction of 23.8 based on the mole fraction right there. Okay, so now this is non-ionic because sugar did not split up. Now let's do an example where it splits up and see how the ions can affect. So before this, when we were doing calculations with ionic stuff, we always had the I, M, K, F stuff, right? And we just multiply the I there. So somehow the splitting of ion here will affect our mole fraction. So I want to show you that in the calculations. This is a very, very commonly missed problem where people see the moles of ionic compound here. They put just the moles of ionic compound. You actually don't do that. You have to put in moles of ions because the ions split into its own entity. Okay, so let's go ahead and do the next one where we're going to calculate P of solution containing ionic non-volatile solute. Okay, so earlier was non-ionic, non-volatile. Now we're going to do an ionic one. So how can you tell? Well, here's the question. A solution of 0.102 moles of CaNO3. You guys know the name of this? You remember naming? What if I started writing all in just formula names and you had to like write your own formula out? Could you guys do that on a test? Like, I mean, that's stuff you're supposed to already know, but I'm just saying I'm probably not going to do that. But sometimes it comes out like I just say the name or I say the formula. It's assuming you already know the other part. Okay, like this one here, I wrote CaNO3 too. If I wrote calcium nitrate, it would literally mean the same thing. Okay, so sometimes I say out calcium nitrate, I write this because I expect you to already know what it looks like. Okay, and 0.927 moles of water. So that's the solution here. We have calcium nitrate is non-volatile because you don't see like just salts just turning into vapor. It doesn't do that. But water can vaporize, right? Water can vaporize at any time. So it says here the question, calculate the vapor pressure of the solution at 55 degrees Celsius. The vapor pressure of pure water at 55 degrees Celsius is 118.1 torr. You guys remember in Chem 1 when you did a lab for gas, ideal gas law lab, you had to look up your chart where the different temperature, you had different vapor pressures of water. So this is why the water, they have to state the temperature because every temperature is a different number. Like you saw how earlier 25 degrees was like 23.8. This is 55, it's 118.1. So it's different at every temperature, okay? But then that goes back to the fact where we knew the curve goes up on the vapor pressure curve, remember? So as you increase the temperature, the vapor pressure does go up. That's why this number is so much bigger. It says here, assume the solute completely dissolves. So when it says completely dissolves, that means you need to know how many ways it splits. If you got this many moles of this compound, how many moles of ions do you have? That's why it's telling you that it splits completely. It's completely on the water, they're all in ionic form, okay? So how many moles of ions do we have here? We have 0.102 moles of calcium nitrate. How many moles of water? Moles of water. How many moles of calcium? How many moles of ions is this? How many ions do you get from 1 mole of this? How many ways does it split? 3. Right, very good. So that means instead of putting 0.102 moles for your mole fraction, for moles of compound, you're going to split into moles of ion. So remember, you got to do times 3 for this number here. Okay, so let's go back to our formula. P of solution equals to P of solute and solvent. But again, in our case here, our solute doesn't really have a problem there. It doesn't exist. It doesn't turn to gas. But the moles of the solute does matter because we will be using mole fraction here. Okay, so P of solution, again, now goes back to mole fraction of solvent. That equals to mole fraction of solution. So solution and solvent is the same thing now. Okay, so I'm just going to do P of solution equals to P of solvent. I meant to write the solvent, which the solvent is water, okay, in this case. How did you know it was 3? Yeah, because this is calcium 2 plus, hopefully you remember that, and nitrate negative. And there's 2 of them according to 1, 2, 3 ions, okay? So mole fraction solvent times original vapor pressure of the solvent. So we have the original vapor pressure for that one. It's 118.1 torr. That's the water. We need to find a mole fraction of water, okay? So to find mole fraction of water, what's the formula? You take moles of water divided by moles of water plus, in this case, not moles of calcium nitrate, you gotta put moles of ions. That's the difference. Earlier, we were just doing the whole compound, right? Because it didn't split. But because this guy splits, you have to do the moles of ions split up. Okay, so that's the difference here between an ionic compound versus a non-ionic compound. So let's go. And that's a really common mistake. People do that all the time because they forget to do the ions on the bottom. And the answer for without the ion splitting on the bottom is in your answer choices. So it's very easy to just completely miss it without realizing you missed it. Okay? So make sure if you see an ionic, make sure you put moles of ions on the bottom, it splits. So let's go for calculating the moles if we need to. We already get the moles of water. That's good. We got a moles of that. So we don't even have to calculate. So let's put in numbers. 0.927 moles on the water on the top. 0.927 moles of water on the bottom plus moles of ions. Is it 0.102? Do you use 0.102? No, you don't do that. You take 3 times 0.102. So you do 306. Okay, so let's see. We get a mole fraction 0.7518. And that goes up here. So we'll put 0.7518 up here. And then times 118.1, you should get your answer of 88.8 torr. All right. So hopefully you guys remember all this. I know there's a lot of stuff like you already learned Chem 1, and sometimes, well, I guess it's assumed that you know that stuff, but if you don't remember, you need to ask so we can like go over it, kind of like a fresh review, talk about what chapter it's from. But That's how we would do something with ionic. So we already did the two types of solid, where the solid doesn't turn to gas, right? How about we do one where now the solute turns to gas and the solid turns to gas? You need to do both portions of it, okay? So we're gonna do an example of that. Now, so we're gonna do calculate P of solution where both solute and solvent are volatile. Both of them will turn to gas. And actually the question is pretty long. Well, I'll write the question here and we'll work the problem on the next page, okay? You guys go with that? Because it's gonna take a few lines here. All right, let's write it. A solution contains 3.95 grams of CS2 and 2.43 grams of acetone. Acetone's formula is CH3COCH3. The vapor pressures, so here's a big hint, they'll tell you the vapor pressure. There's the vapor pressures at 35 degrees for pure CS2 and acetone, pure acetone. See how they told you the original vapor pressure? That's a hint that both of them will turn to gas. Are 515 torr and 332 torr, respectively. Okay, now it says here, assuming ideal behavior. So I have to tell you what ideal behavior means. Calculate the vapor pressure of each component and the total vapor pressure above the solution. We experimentally determine total vapor pressure of solution at 35 degrees Celsius is 645 torr. Is this solution ideal? The ideal solution tells you that P of solution, this is what ideal solution, the formula tells us ideal solution. P of solution is P of solute plus P of solvent. Now sometimes what you calculate for ideal doesn't match what you do in lab. Okay, we'll see if it matches. They're asking you, does it match what you calculate basically? They have what number they got from lab, from experiments. And then based on that number, we compare to what we calculate and we'll see how it varies or if it's the same, if it's ideal or if it's non-ideal and kind of look at what the difference is, okay? I'll give you guys a few seconds here to write. Is the calculation always in torr? No, not really. It doesn't have to be, but we tend to use vapor pressure in torrs a lot. Like the common units we have in this class will be torr, ATM, and millimeters mercury. But a lot of them will be mentioning torrs. But if I put millimeters mercury, you should know the conversion, right? 760 torr is 760 millimeters mercury, and that equals to 1 ATM. For the names, what chapter? I think it's chapter 2 or chapter 3 in Chem 1, okay? So you can take a look at the slides I posted. And if you guys need a review, take a look at those notes and we'll talk about naming and stuff. And also, of course, when you guys were naming stuff, you have to know your polyatomic ions as well. All right, so let's go ahead and do this part. Now we have both solute and solvent together. So to do this, we definitely need moles of this guy and moles of that guy. Agree? We need to get moles because we need mole fractions of both of them. Because what you're going to need to do is you're going to do P of solute is something, P of solute is something. So what's P of solute? It's going to be mole fraction of solute times the original of solute. And this one is going to be mole fraction of solvent times the original of the solvent. Okay, so we have two parts here that we got to do. So what I want to do is go ahead and figure out the moles for both of them first so we can figure out who's solute and who's solvent. It really doesn't matter because both of them are going to be in there. But you got to be able to figure out the moles. Okay, so let's go ahead and do that. I'll write down the molar mass for you guys as well. Everyone done writing this question? By solution doesn't mean 645 torr. Yes. So it says here the total vapor pressure of a solution of 35 degrees is 645. Now this is experimentally determined. So this is a second portion of the lab. The question. It says the first part of the question tells you, go ahead and calculate it on your own, assuming ideal behavior. So this is ideal behavior, assuming it fits exactly these numbers. This is what you'll calculate. And they're saying, based on the number you just calculated, this is what we found in lab. Is the solution ideal? If it matches what you calculated, if you calculated 645, then yes, it's ideal. If it didn't calculate 645, then it's not ideal, and then we'll talk about that, okay? You're welcome. All right, so let's turn the page around. Yala, if you need me to still let you write some more. I always complain I write too fast. So molar mass of CS2 is 76.15 grams. Now, if I don't give you the molar mass here, you guys know how to get it from your periodic table, right? And you will have a periodic table for every single exam. It's on every single page of your test. So molar mass of the acetone is 58.08 grams per moles. You see, you notice how I write MOL, I don't write M? It's because MOL is the abbreviation for moles, okay? Such a common misunderstanding for some reason. All right, so we have that. Let's go ahead and get the moles for both of them. We had the grams. CS2 was 3.95 grams. And acetone was 2.43 grams. So 1 mole. 1 mole of CS2 is 76.15 grams. I will take 3.95 grams times that. 1 mole divided by 76.15 grams. I guess it's basically divided by the molar mass. I don't like to memorize stuff. I just like to put numbers in and cancel stuff out. But sometimes the question gets really, really complicated and there's a lot of steps. I just like to do it methodically without having to memorize any formulas ever. Well, as much as I can avoid it. All right, so we got this. Let's get the moles out. While you guys do that, I'll set up the next one. 2.43 grams of acetone, 1 mole of acetone weighs 58.08 grams of acetone. All right, so looks like you're both small numbers, but you have more CS2 than you have acetone. I'll write it out. 0.05187 moles of CS2. And then for the acetone is 0.04184 moles of acetone. So technically, the definition of a solute and solvent, the solute is a smaller portion, the solvent is the bigger portion, if both of them are liquids, right? So technically, this one's the solute, that one's the solvent. So acetone is the solute in this case. But we have to calculate both anyway, so, okay, so let's go ahead and do mole fractions, okay? So we can do mole fraction of CS2, which in this case will be our solvent, will be moles of CS2 over moles of CS2 plus moles of acetone. Correct? So that will give us an this is like almost half and half, but this is a slightly bigger half. So this one, when you put your numbers in, let's go ahead and put it in. We get 0.5535. Okay, now that's one. Now, here's a trick. If you know your solution has two parts and you know one portion of it, so basically you have a pie chart about this much is CS2 and this much is acetone. And the total of them equals to what? 1, okay? So basically this is, if this was 0.5535 and the total is 1, how much is this one? This portion. This would be 1 minus 0.5535. Agree? That's a shortcut. Now you could have done moles of acetone over moles of CS2 moles of acetone. You get the same number. Okay? But sometimes when you get that, you just subtract and you get the same answer. Okay? So just an idea there. You can do that. Now we have both portions. Okay, so you could have done moles of acetone over moles of CS2 plus moles of acetone for this part and got the same answer. So let's keep going. So now we have both of the mole fractions. Let's go ahead and put everything together then, okay? So we want to do P of solution. We know it's P of solvent and solution together. So we said that this was a solvent, this was solution, solute, right? So P of my solute, no, my solvent. Oh my gosh, there's so many words here. Solvent. And then P of acetone, which is my solute. Okay, and I need a mole fraction. So mole fraction is 0.5535. This is for CS2. And then what's my original vapor pressure of CS2? Let me look it up. Original vapor pressure of CS2 is 515. Okay. And then you gotta do the acetone portion that goes over here. This one's solvent. Mole fraction is 0.4465 times the original earlier is 332. Okay, so we'll have both portions now. You get 285 here, and you get 148 here. And the total of these two will be 433. Now this here is for an ideal solution. Okay, 433. What did they get in lab? P of solution, experimental. In lab, okay, they got 645 torr. So the solution is not ideal. Okay, so let's go ahead and write it down. And I want to explain to you how it's not ideal. Well, just kind of looking at the observations. Not ideal. It shows a positive deviation. It's bigger, right? So with it, it shows, I can't spell. Deviation. Okay, what does a positive deviation mean? Let's take a look at some pictures. So don't like be a little scared by it because sometimes you see lines, you're like, oh, I see lines, it doesn't make any sense to me. But let's just imagine it, okay? So here's the picture, it's from slide number 47. Ideal was non-ideal. So this was ideal. Pressure of A, pressure of B, when you add the blue and the blue and the red, you get the purple. That's ideal, a straight line, okay? What happens if you have strong solute and solvent interactions? That means compared to the ideal solution, your vapor pressure is actually lower than expected. Why is it lower? The reason why anything is lower is because they like the new buddies a lot more than you expected. Like if water bonds with some other solute and it really, really likes the solute, it has less reason to turn into gas to create the vapor pressure. So if you have a negative deviation, it indicates a strong solute-solvent interaction. They like each other a lot. Okay, the formation of solution is really, really, they're really happy to have new friends there. Now, the one that we just saw was actually higher. A positive deviation from a straight line, that means there is a weak solute-solvent interaction. So if you assume like maybe CS2 and acetone likes each other for a certain amount, but the calculation, the lab experiment shows that it likes each other less than what you thought it should. Okay, the solute and solvent interaction is weaker than expected. That's why it's a positive deviation here. Are we all clear? So that the positive versus negative, it kind of shows you if it likes each other more than ideal or if it doesn't like each other as much as the ideal. Okay? So in this case here, because it's positive deviation, that means it's a weaker than expected, than ideal. Weaker than ideal solute, solvent interaction. Okay? Any questions so far? Are we all good? Still alive? Hopefully. Okay. You made it through Chem 1. I'm sure you can survive this. This is just math. All right. So the next part, I want to talk about osmosis. All right. You guys done with this? I'm going to turn the page over. Actually, let's see if we can do a poll today right now. Let's see. I have to make some new polls. Okay, so here's the funny one. Since we live in Florida. It's not that funny, but I'm curious. Do you guys see the poll?
Yeah, I can see it.
You want to know something funny? I've lived in Florida so many years. I have not been to Disney.
Disney is awesome.
Oh, that's what I hear, but I've never been. You know why? Because I hate lines. Are there lines all the time when you go to Disney?
There are. The lines are pretty unbearable. I'm not really a big fan of like theme parks in general.
Oh yeah. See, what I do is I got the was it the Premier Pass to Universal. So I just go after 4:30 and I walk on the line, no lines, just walk on it. If there's line, I'm coming back another day.
Yeah, I was about to say the only time it's like pretty bearable is like if you have a fast pass and you can just like move through
Right?
the line.
Doesn't the
Because
fast pass like get booked up like months ahead?
yeah, it's insane. That's that's one of the reasons I like never go to Disney
And
because
that's
I'm
the
like,
reason why I've never been to Disney. It's kind of funny. I live in Florida for so many years. I've never been to Disney, but it's the truth. So, as you can tell, I like Harry Potter a lot. So I go to Universal for that. I don't like crowds either. I only go when it's not so busy. So
I think Islands of Adventure is better than both of them.
which one
Islands of Adventure is better than both of them.
isn't that like part of
I was
Universal?
about to say I kind of consider that like in Universal, like there's
Yeah,
Universal and Islands of Adventure, and they just sort of
because
connect.
Disney has like 4 parks and Universal has like 3 right now. Studio Ghibli. I've never heard of it. Where is that? Okay, so anyway, for people who are watching, they have no idea what we're talking about. The poll was Disney or Universal. Is Disney 16%, Universal 43%, both 32%, neither 9% because they want Studio Ghibli. I've never heard of that. Where is that at?
That's like a movie company, like in Japan. So is there like a theme park for Studio Ghibli?
Yeah, I have no
I
idea.
heard they're making it, like they're opening one, but not as of right now. But the animations made my heart over Disney and Universal movies.
That is cool. I actually like all the animation stuff too, so that would be cool. You know what they're building? I heard they're building was it Nintendo Mario stuff at
Oh my
Universal?
God, I'm so excited for that. I'm so excited for that. It looks
Me
so cool.
too. Anyway, yeah, that's the only game I like. I'm good at playing at the Mario because I'm old like that. But and we play like Tetris, Super Mario Brothers. Yeah, I can do that. All the other stuff, I'm like, oh, Busch Gardens. You know what's funny? I've never been to Busch Gardens either. I don't think. I must be missing out on Florida life. Anyway, all right. So one person didn't vote for some reason. I hope you guys are paying attention. But anyway, I'm going to go ahead and end the poll here. Share the results for a second. And you can see Universal wins. So I can do more Harry Potter stuff. You only went to Busch Garden once and it rained. I know, how terrible is that? So you know what's something about rain that I've experienced is my first football game ever went to for college football game. It rained and I hated football for the longest time because it was so traumatic. You had to evacuate because of lightning. But then after a while I started watching it and I like football again. But yeah, rain can really dampen stuff, especially when all the rides are shut down. Anyway, so we're going to talk about osmosis here. You guys remember the previous poll we said you guys are going to sleep on your textbook and hope to learn? Have you guys heard of people saying you want to sleep on your boat, you'll learn via osmosis? You should really say using diffusion. Why? Because osmosis is the movement of your solvent, the water portion, right? Not the diffusion is the movement of the actual solute stuff. So it's from high to low. So if you were saying you want to sleep by learning with osmosis, sleep on your book, and say the knowledge is the solute, and it's going to move, osmosis is just going to move the brain matter around or the book stuff. Anyway, it doesn't make sense to say osmosis. You should say diffusion because you want to move the knowledge from the book into your brains. But that's osmosis. Osmosis, when we learn osmosis, is basically trying to even out on both sides. So you have high concentration and low concentration. There's always a tendency to want to move things. So you have equal concentrations on both sides and you're moving the solvent. So over here, here's a picture of it. So you see how there's water and there's solute, they want to go ahead and mix it up because the water is going to travel towards the higher concentration side. Okay, so this is the movement of the solvent. So the pressure that is required to keep the osmotic flow from flowing naturally is called the osmotic pressure. So this is pi here, osmotic pressure. All right, so what's the definition of it? It's called the pressure needed to keep osmotic flow from taking place. All right, in my formula, we're gonna do pi osmotic flow is I m r t. So this one here is going to be, you know how earlier they kept using torr? A lot of times they use torr or ATM here, whatever. But whatever the unit they gave you, you want to convert it to ATM. There's a reason why, okay? They'll give you in torr, millions mercury, whatever, but you will use ATM because this here R is your gas constant. And the unit for gas constant is liter ATM moles Kelvin. So you have to match your units with this guy. And remember the constant here is 0.08206. If you don't remember that, it will be on your periodic table. But you should recognize this is gas constant. I here is what? The Van Hoff factor, right? If it's ionic, how many times it splits into. M here, notice this is capital M now. This is molarity. Not molality anymore, it's molarity. So it's moles of solute over liters of solution. And T here will be temperature. And what do you think the unit should be here? It should be in Kelvin. Because you see how Kelvin crosses off moles and liters, crosses off, ATM crosses off. So those are the units, they all match this guy. Okay, so if the question gives you a different units on purpose, they'll give you Celsius, they'll give you torr, and if you don't convert, you'll get the answer wrong. All right, so let's continue with osmotic pressure from last time. We were saying osmotic pressure is the pressure you need to make sure the osmotic flow stops. You can't, otherwise it will just take place on its own automatically. So the important thing is, this is pi, the pressure. You will use it in ATM when you're calculating. If they give it to you in a unit other than ATM in a question, you convert it to ATM. Okay, why? Because we want to match the unit on the gas constant. So you need to remember where to find a gas constant on a periodic table. You should be able to see it on the practice test. I think I uploaded, no, I did it for the lab. So if you guys want a copy of the periodic table, I'll show you guys. So you have this ATM, and then molarity here, moles per liter, so moles in liter over here. Temperature must be in Kelvin. The question will give it to you in Celsius maybe, or Fahrenheit, usually Celsius. Or if sometimes they give it in Kelvin, but always use Kelvin in your calculation. And then I here is your Van Hoff factor, okay? So let me give you a question here. It says the osmotic pressure of a solution containing 5.87 milligrams of an unknown protein per 10 mils solution is 2.46 torr at 25 degrees Celsius. Find the molar mass of the protein. All right. So to do this, your target is to get the molar mass. So what's the unit for molar mass? It's like something is 10, like 8 water. Water is 18.02 grams per moles. Agree? So it's grams per moles that you're looking for. So always write it down. That way you know what you need to do, okay? Like you need to find grams somehow, and you need to find moles somehow, and then when you put them together, you get molar mass. So is there anywhere here that we can find grams of a protein here? Because they want the molar mass of the protein, so you need to find grams of protein. Well, yes, look here. This is in milligrams. You can easily convert it to grams, okay? So that's what you want to do. So they tell you there's 5.87 milligrams in every 10 mils of solution. They tell you 5.87 milligrams can be found in 10 mils of solution. Okay, so that's the thing that we have. So we'll take this part here and we're going to convert this part to grams. Okay, now, and the next thing is like, well, what about the moles portion? How are we going to solve for the moles portion? So that one's not as obvious. We do know there's 10 mils of solution, correct? Okay, and we do know the osmotic pressure is this, and we know the temperature is that. Do you notice how the unit does not match? See that? So that's when you start converting your units first. So the idea here is a protein doesn't split, it's not ionic, so when Hall factor doesn't play a factor, it's just 1 here. And then you can get your R. Your R here is 0.08206, okay? And then you have your temperature, you have your pressure. We can solve for a molarity here. That's what we're after. Once you get your molarity, it's moles per liter. Well, you have 10 mils. Take that, coupled with the molarity, you can get moles of your protein. Okay, so that's what we're gonna do. I'm gonna go ahead do the conversion of the units first. So we'll have to convert 2.46 torr to ATM, right? So okay, go ahead and do the math here. So what's the conversion between ATM and torr? ATM, I'm gonna switch it so it's up here, torr on the bottom. It's, you guys remember 1 ATM is?
760.
Very good. So it's very, it's like small things here that I said, okay, you have to remember 1 ATM, 760 torr, 1 ATM is 760 millimeters mercury, okay? So let's do this, and you can get a really small value for your ATM now. That's okay, we'll keep that number. So that's what we have for our ATM. And then we also want the temperature converted. So 25 Celsius, we need to report it in Kelvin. So it's 25 plus 273 here. We get 298 Kelvin. Okay, so now we have ATM, we have Kelvin, and we know R. We can solve for molarity. So I'm going to write the formula here. It's not ionic. Proteins can't split like ions, so that's a 1. Let's put the ATM down. This is 3.22 times 10 to the minus 3 ATM equals to, I is just 1, doesn't split. M is what we're looking for, molarity. R is 0.08206. The units are liter, ATM, per moles Kelvin. And then you gotta put your temperature in, 298 Kelvin. Let me solve for molarity here. So let's see. So molarity is basically this term divided by all these guys, all these 2 in the bottom, okay? So you can hit this and then divide by that and then divide by that again, or you can multiply this term and then take that divided by the multiplication of this. So what did you guys get? I want you guys to try doing this on your calculator. It seems really silly, but let's see what you guys come up with. I have students who don't know how to put this in the calculator still, and they don't remember how to put brackets in between different operations. So I want to make sure you guys are able to do that, okay? Always use the calculator you are using for your test. That means you use a non-programmable one. If you have a TI-83, 84 plus whatever, those are too fancy. You want to start getting the cheaper ones, the 15-buck ones, okay? So I got, let's see what you guys get. 1 point, Did you guys get that? Okay, so if you didn't, so let's see how you guys are doing it. You do have to put brackets in when you do these two terms, and I don't know how you guys are putting this value in. So are we able to get this? I'm going to show you guys how I do it on my calculator, okay? So what I like to do is, there's a few ways to do it, but the way I would do it is, I would take this and that, multiply that together, so, right? Just do that, and then hit, that's the answer, that's one part. Okay, and I don't round at all. I take that number, I'm gonna take 3.22, 10 to the, so when you do 10, I do E or EE for you guys exponent. Whenever your calculator is a little, mine's different than yours, so that's why you have to learn how to use yours, okay? 3.22, 10 to the power negative 3, so that's how I did mine. See how I didn't round at all? I kept all my numbers in the calculator, right? So, and then I just take divide, I recall my answer back from previously, and then I get that. So 3167, so I guess it's 31, it should be 7 here, put it wrong.
Yeah, that's what I got, what's on the calculator there,
Yeah.
not the 8.
Okay, great. So, you know, like, I like to just go ahead and do it straight on the calculator without rounding, especially in lab, do that. That way you have less error, and then you just keep your sig figs at the end. Okay, so technically I could write 6, 7, 6, 4, 4, 5, 6, but I didn't bother writing all of it, so let me fix this with 7. All right, so everyone good here so far? Now, the next thing is, once we got molarity, so we know that molarity is 1.317. It's really 1.32 at this point, but times 10 to the minus 4 moles, okay, per 1 liter of the protein. Now, do we have the volume of the protein? Yes, we do, okay? So you take that 10 mils of your protein, convert it to liters, and then use your molarity to get your moles of protein. So 1 liter is 1,000 mils. And then we know that moles is 1.317, 10 to the minus 4 moles of protein per 1 liter of protein. That should give me moles of protein, okay? So in that case, we will get 1.317 times 10 to the minus 6 moles right here, okay? Oh, okay. The gas constant, there's 2 of them. We will be using both this semester, but just remember, if you're not doing anything with energy for the gas constant, don't use the gas constant that has joules, because joules is for energy, okay? So if you're not doing anything with energy, just stick to the liters, ATM, moles, Kelvin one, all right? So I'm glad we figured that out. We used to how to do on a calculator here. So the moles is what you get here, and then we just plug that moles back over here, and we can get our molar mass that way. Okay, so 5.87 milligrams turned to grams is 10 to the negative 3. Remember, like, I guess I'll just work it on the side here. 5.87 milligrams. 1 gram is 1,000 milligrams. So it equals to 5.87 times 10 to the minus 3 grams. Okay, so that's that gram portion that I'm going to put up here. And then you're going to divide by the moles, which is 1.317, 10 to the minus 6. So we keep 3 sig figs, 4.45 times 10 to the power 3 grams per mole. Now, it's really common for proteins to have heavy molar mass, so that's normal. So everyone follow so far? So you probably see this in your homework and potentially on your quiz as well, and on your practice test, on your real test. So something like this is pretty common. Sometimes you get it, sometimes you don't. It depends on the test version that you get, okay? Just make sure you are able to do it if they come up with something like this. All right.
I have a question.
Yes, question?
I was just 0.02 off. I got 4.43 times 10 to the third. Would that be marked wrong or just given off
What do you
point?
mean you got 4.43 here?
Yes.
What did you use down here? Did you round a little bit?
Well, I started out where my numbers started looking a little different than yours is when I got right at the beginning when I divided 2.46 by 760, I got 0.00323. So I got 3.23 times 10 to the negative third.
Yeah, it's not gonna matter that much. And you gotta remember for if you're doing homework, they have a little error bar. Like if you're like 4.43, 4.44, they'll still take it.
Okay.
Like it's close enough. For our test, it won't be an issue because it's gonna be multiple choice. So you pick the one that you know possibly is really, really close, but not the same, probably because of rounding.
Okay.
Okay?
Okay, thank you.
You're welcome.
I have a question, please.
Uh-huh.
I keep trying to put it in the calculator at step when we were doing the 0.08206 at that first step.
This
Yes,
here?
and it's not coming up at all.
It depends on your calculator. You might have to do a bracket.
I tried brackets and without it because you're multiplying those two numbers, then you're dividing by 3.22. Is that correct?
Here's another way you can do it if you don't know how to do the bracket. So you can do 3.22 10 to the negative 3, okay? That's the answer right there. And then you can divide these two numbers separately. Take that, divide by 0.08206, okay? Hit the answer. And then you divide by 298. You get the same answer. So there's many ways to do it. If you feel like you can't do the bracket part, sometimes this stuff helps a little bit. So you just want to get comfortable with using your calculator.
Okay, thank you so much.
You're welcome. All right, so let's keep going. What's it gonna do? Oh yeah. So I want to talk back about the Van Hoff factor. You know how Van Hoff factor was like how many ions it splits into, correct? So every time you see a formula, you should be able to predict what the I is. Agree? So let me zoom in a little bit. So if I see non-electrolyte like protein or sugar, we expect it to be 1, right? Because it doesn't split. And then if you do it in lab, you can measure the I and calculate a number, okay? So that basically, if you wanted to do the measurement of your I, you will basically know what your KF is exactly, which we do. We know that KF is a constant. And then we will know the molality of your solution, and you can calculate for your I based on your delta TF. Now, a lot of times what they end up observing, NaCl, you look at this and you're like, well, that's 2 ions, so I should put 2. But if you do it in lab, you find that it's a little bit smaller than 2. It's 1.9. If you do this guy, so MgSO4, how many ions does it split to? It's magnesium and sulfate, okay? So it's 1 and 1, so that's 2 here. When you do it in lab, you notice it's less than 2, it's 1.3. So what in the world is going on here? Okay, so you see here MgCl2, there's 3 ions, but when you do the experiment, you see it's actually smaller than 3. So there's something happening here. This is called ion pairing. So basically, what happens is when they split into ions like the plus and minus, well, this is plus and that's minus, and then they get flanked around the water molecules because of ion dipole interaction, right? Now, when they get flanked around ion dipole interaction here with the water surrounding it, sometimes they cross each other here and they're like, hey, we used to be really best friends. So they kind of like pair up, even though they're separated and covered by water. They pair up a little bit as an ion. It's not really a whole full like intermolecular forces, but it's kind of like an attraction there. So it's weak. But essentially, if you have enough of those ion pairing happening, you actually can lower your Van Hoff factor because they're not completely split up. They're still like, hi, I used to know you. Let's still be kind of friends. Deal. Okay, so that's ion pairing. Ion pairing basically says that, you know, sometimes the number in lab is actually smaller than what you predict for a Van Hoff factor. So over here, we talked about all this, so we should be good. So let's go ahead and see an example where we do have ion pairing. We can compare, we can see the formula and know what we're supposed to get, but know that when you calculate, it's going to be slightly smaller due to ion pairing, okay? So let me go ahead and change page. It's not stupid. All right. So let me write the question now. The freezing point of an aqueous solution of 0.050 molality CaCl2 solution is negative 0.27 Celsius. What is the Van Hoff factor for CaCl2 at this concentration? The reason why they say it at this concentration, because the more concentration you have, the more ion pairing it will have, okay? Because, you know, there's more of them, they're more likely to pair up with each other. How does this compare to the expected value of I? KF water, we'll assume it's 1.86 here. So let's see how we're going to do this. So what's my delta TF? That's the freezing point, right? So remember, delta TF is the drop from 0 all the way to negative 0.27, and it's the absolute value. So I know my delta TF will be 0.27 here. Okay, so delta TF equals to I M KF. We know what the I prediction will be, but we're calculating for it. Okay, what's the predicted expected value of I, it says here, if you have CaCl2?
3.
3, very good. So we expect to get something close to 3, but not quite. It's gonna fall a little short under due to ion pairing, okay? The molality here is pretty small. Now we'll notice the higher the molality is, the more ion pairing will happen, the smaller it will drop to be a smaller value. Okay, so let's go ahead and plug it in here. So 0.27 Celsius equals to I, we don't know what it is, we kind of know it's going to be around 3. And then 0.050 molality, KF 1.86 Celsius per molality. Okay, we solve for I here. Again, the same way like we were doing the math earlier, but these are easier numbers. So you take 0.27, you can divide by 0.050, and then divide by 1.86. You should be able to get the same answer. Okay, so hopefully, yes, 2.9, very good. So 2.9, and our expected, like we said, was 3. So why is this smaller? It's because of ion pairing, okay? All right, so that is actually pretty much the end of the stuff I want you guys to learn for chapter 14. So make sure you guys start working on your homework and doing your extra credit stuff, okay? So the next topic, we are going to go into chapter 15. We're going to be talking about kinetics and how fast things go. So can you tell me something about like how do we measure how fast things are? Like just an example, like I think the homework question didn't have the KF value for this question. On the homework on mastering, they expect you to look up the constants and stuff like that. So there will be a link to some tables. And you click on the link on the top in your homework questions and you can pull up the KF that way. Okay, but you do know that KF for water is 1.86. Was it like in lab it was 1.853? So it's around that number. But in our notes we have it as well. So it's open both during the quiz and the test, so you should be able to use it. And on your test itself, the test is not open book, but on the test itself, you will be provided that in the question. Okay, so there will be ways to look it up if they don't give it to you directly. But on the homework, they expect you to be able to use the table. So you want to get comfortable clicking the links on the top there.